Welcome, everyone. We'll go ahead and get started. As you see, it's a fairly small group, so we can be a little informal. If y'all want to stay in the back, that's cool. But it looks a little weird, just saying. That's fine. Hey, my name is Tom Newman. I'm the project scientist on ICESat-2, and at the outset, I'll do a little mission update, kind of 8 slides or so. But the real applications that you'll hear about are from the 4 speakers in bold: Dr. Neil Weston, Dr. Zbradanandi, Ross Smith, and Dr. Douglas Comer. They're all online. They're all here via Zoom, and we'll just run the slides from here. They'll say next when they want the next slide, or make sure I play the movie or what have you. And then we can have a conversation at the end, especially given the size of the group here. Very good. So I think without further, go ahead. Yeah, are there other folks online, Molly? Yes, there are. Yeah. Awesome. Thank you all online for muting your mics. It's no excuse. We're 2 years into this. Everyone should know to mute their mics when they dial in. Is there any further ado I should do, or without further ado, let's do this. So yeah, my name's Tom. I'm project scientist of the ICESat-2 mission. I'm at NASA Goddard, assisted ably by my deputy, Nathan Kurtz. And Lori Magruder from the University of Texas at Austin is our science team lead. And what I'll end up presenting is not solely my own work, of course. It takes a small army to make one of these missions happen and to keep it running. In case you're unfamiliar with ICESat-2, can we get a show of hands of at least folks here who are unfamiliar with ICESat-2? Good. All right, a few folks. Awesome. ICESat-2 is a laser in space. It's a LiDAR. It carries a single instrument called ATLAS. ATLAS uses green laser light to measure the height of the Earth. And the way it does that is ATLAS generates a single laser pulse, green light, on board, and splits it into 6 individual beams as that laser pulse leaves the spacecraft. On the ground, it makes a rectangle pattern of 6 spots, and as it cruises along in its orbit, those spots describe tracks on the ground. The rep rate of the laser is 10,000 kilohertz, so it sends out 10,000 laser pulses every second in each of its 6 footprints, and those footprints are each 11 meters. With that rep rate and at our altitude, that means we generate really dense sampling in the along track direction. That those footprints are spaced at just 70 centimeters along track, so there's a lot of overlap. But you can see it makes a fairly sparse data set, really dense in one direction, pretty sparse in the other direction with the gaps between the beams. I should also say that what ICESat-2 detects as that light reflects off the surface of the Earth and back up to the spacecraft are individual green photons. It's a photon counting LiDAR. So the base data product for ICESat-2 is a latitude, a longitude, and a height of each of those photons that ATLAS detects. It downlinks information on what time the laser pulse left, what time photon was detected, and a few other bits of information to let us generate those latitude, longitudes, and heights. ATLAS and ICESat-2 has been on orbit for just over 3 years, 1,187 days. ATLAS is doing great. It's operating nominally. We just crossed 1 trillion laser pulses from the ATLAS instrument on November 1st this year. So I think we're now up to 1,038 billion. Turns out 10,000 shots a second times 86,400 seconds a day makes a lot of data in a short amount of time. Yeah, and our data go from 88 degrees north to 88 degrees south as by virtue of our 92-degree inclination orbit. So it collects data nearly globally, just those little pole holes at the high latitudes. But yeah, all is well up in space, and ATLAS is doing great. Our data products, as many of you know, are all served through the National Snow and Ice Data Center. And the product I mentioned earlier that provides a latitude, a longitude, and a height of individual photons, that's the ATLO3 product, far and away the biggest product that we have. There are many parameters at the photon rate, and over the first 3 years of the mission, those ATLO3 data products contain information about the 12,460,000,000,000 photons that ATLAS detected and transmitted to ground. It makes that product a little unwieldy. So if you can get by and use one of the higher level products, please do. They're much easier to use. They're much smaller. And we have surface specific products for land ice, for sea ice, for land and vegetation, and so on, all of which are available through NSIDC. And we just released version 5 of these products about 2 weeks ago. So far, since we did our first data release in May of 2019, we've had some 4,000 plus registered users who collectively have downloaded 19 million data files, which is awesome. That's why we do this. Those data products come out at about a 60-day latency. We do it in batches of 6 weeks. So if you're waiting for some particular data, that's usually about 6 weeks of latency. I mentioned that those along track products are version 5. And higher level products that take those individual passes and grid them are in initial versions. ATL 16 and 17 are gridded atmosphere products, and that's up to version 3. ATL 14 and 15 were released today, and those are your gridded ice sheet products. So they're collecting up all of the data over Greenland, all the data over Antarctica, and we'll see some examples here in a bit. And then ATL 19 is at version 1, and that's the gridded ocean product. So all the data over the world's oceans. And then 22 is our inland water gridded product. That's coming by the end of the month. And those will be easier to use yet. As I mentioned, those final data products have about a 60-day latency, and that's too long for many applications. So we've been working with a group called the Satellite Needs Working Group, or SNWG. And the purpose of that group is to connect missions like ICESat-2 with end users and other agencies that could benefit from these products if they knew about them or if we made some changes to how we do things. So we've started producing and will soon be releasing what we call quick look products. These are about a 3-day latency, and they don't have the best possible final geolocation or heights on them, but they're pretty good. The first 2 products we'll release are sea ice elevation and the atmospheric profiles, ATL 09, and there's a handful of products that'll come later by the end of this year. The main differences between the final best products and these quick look products are in the reported heights. The quick look products, by our analyses, have lower heights than the final products by about 2.7 meters for hashtag reasons. Be happy to go into if people are interested. And the reported locations in those quick look products aren't as accurate as in the final products. These quick look products have a larger standard deviation of the error in their position, about 10 meters in the cross track direction and up to 100 meters in the along track direction. I'd be happy to talk about that if anyone is interested. So, okay, a couple data product examples. This is our gridded ocean topography product, which just was released last week. This is the mid-latitude grid. You can see the domain there. It's posted at 1/4 degree grids and aggregates data over an entire month. This is over September 2019, and you can see the ocean topography and how the different currents are manifest in the surface height variation. And that's at release 1. ATL 14 and 15 I mentioned. 14 is your land ice DEM. That's a DEM for January 1st, 2020. And what ATL 15 adds is the height change since then. So if I play the little animation, you can see time reported in the upper right there, and the color represents elevation change, red being elevation dropping, blue being elevation increasing through time. That just accumulates over time. Posted at 1 kilometer grid, and we have a layer for every 1/4 of a year or every season. So far with 3 years of data, that'll give you 12 layers if I multiplied 4 by 3 correctly. Those are released today at NSIDC, and they're pretty easy to use. They're net CDF, and they play nicely with any GIS package that you like using, like QGIS or ArcGIS, or take your pick. What did you do? If you're on Friday, there is a poster presentation specifically on these products that you can go check out. There we go. Yeah, so, okay, we got a whole suite of data products. You don't have to start from scratch. There are many different tools that have been developed through a few different events that are all available through NSIDC and their open repositories. The main one I'd point you towards, derived from a couple of hack weeks that we have where you get a bunch of people new to ICESat-2, get them together for a week and get them up to speed through tutorials. And then by the end of the week, they're doing science with ICESat-2. Now, all those tutorials from hack weeks are available through NSIDC. So you can go through step by step and follow along yourself. If you're looking to just browse around, open altimetry is a great way to do some data discovery. It's a really easy interface through the web, openaltimetry.org, and then a handful of other ones there I can speak to if anybody would like. But yeah, the tutorials from Hack Week's great way to start, and Open Altimetry is a great way to find data. And that's all I was going to say by way of mission update. All is well in space. Laser pulses going out, photons coming back, data sets get bigger and bigger. Yeah, so I think we'll do questions at the end so we can see everybody's smiling faces. But at this point, I'd ask if Dr. Neil Weston is out there and can hear us, or if we can hear him.
Hello, Tom, how are you?
I'm great, Neil. Hey, so I'll be running the slides, so just say next and I'll dutifully click next.
All right, thank you very much and welcome. I'll just take a few minutes to talk about a few of the products that we are working on using ICESat-2 data. These are mainly for hydrographic applications and nautical chart production. Next, please. So we started out by trying to determine the bathymetry of shallow water regions. And so if you look at the image on the right, you can see the surface that we can easily detect. But depending on the clarity of the water and the depth, we can also determine, where the bottom is. So we know that depth. And what we do at NOAA here is to use this approach to fill in areas that are difficult to get to with a ship. It's just too shallow, it's a remote part of the world, or there's some other, we want to do some quality check on the data. Something new we're starting to look at is reef profiling. I think I mentioned this at the last ICESat-2 get together. So the image on the left shows you two tracks, and there's a portion of a reef, if you will. And what we want to do is build up the structure of that reef over time. So as we get more additional tracks, we can get a profile. The profile on the right is from this reef. And so you can begin to build up pieces and you can see what it looks like. That's sort of a cross section, if you will. All the work we do, we do some modeling, corrections, so refraction, we change to regional coordinates where appropriate, and then data that goes onto a chart is put on a chart datum. So usually it's mean low water. Next, please. So the two other areas that we're focusing on, one's rather large and can be controversial, subsidence and sea level change. So the image on the left was built maybe 9 months ago, but we did use ICESat-2 data to make this. So this is New Orleans, Louisiana area, the Delta. And over time, we've noticed that using geodesy, the land is subsiding. So we use the ICESat-2 to determine where the land-water interface is very accurately. And so the goal is to use ICESat-2 data over the life of the mission to see how this area changes. The black dots and smears, if you will, offshore, those are oil and gas wellheads or platforms. And so we have information about their location. And that's just plotted as a reference. You can infer what's taking place, or that's more of a subject of another discussion. So on the right, very simple representation of how we determine the shoreline. Again, you can see the surface of the water, or the body of water. But then you can see a profile of the bottom, as you move to the right. And the beauty about using the ICESat-2 platform is we can get the geolocation of the photons, as Tom mentioned, latitude, longitude, ellipsoid height, and then we can determine where that land-water interface is. And over time, areas like the Outer Banks of North Carolina change rather quickly. And so our goal is to continue monitoring that using ICESat-2 data. We can feed data from a specific polygon into our algorithms. It can tell us whether there's change or not. So that's pretty exciting for NOAA. And of course, it's adjusted for tides and other correctors, if you will. Next, please. So to summarize, these are the areas that we focus on: nautical chart production, again, missing data, verification of soundings, or for hard to reach regions. At the moment, NOAA only has a few hydrographic ships, so they're expensive to move from A to B. So if we can use ICESat data to verify something before we make the final chart, we will do so. Again, shoreline change. So we've picked a couple of regions to monitor. Outer Banks, the Bahamas. We're starting to look at Key West too. And lastly, the subsidence I mentioned in the Gulf of Mexico. We're also doing Chesapeake Bay area, and I think our NASA colleagues are using other sensors to look at how that's changing over time. So future directions, we'll work with our partners, and a big push is to automate as much as we can. And I think, as Tom mentioned, the data latency could be challenging for certain applications. So we're working with our colleagues in NASA to see how we can get that data in a more timely fashion. So thank you, Tom.
Awesome. Thanks so much. Let's see. We're going to wait to the end for questions. So at this point, I'd ask Dr. Subrata Nandi, do we have you out there?
Yes, please.
Great. I'm going to bring up your first slide and turn it over to you.
Yeah. So thank you very much for giving me an opportunity to share my research related to ICESat-2 data. I am Subrata Nandi from Indian Institute of Remote Sensing Indian Space Research Organization, India. I'm also an early adopter of ICESat-2 data. In this presentation, I'll be sharing my experience related to mapping forest height and above-ground biomass, integrating, of course, LiDAR, ICESat-2 data with the Sentinel-1 and Sentinel-2 data. So as you can see that I have done this study in northwest Himalayan foothills of India. So this is basically moist deciduous forest, and it has relatively flat to undulating terrain. The lines basically what you see here are the ICESat footprints, and the dots represents the field points which are collected for collecting location of the field points for collecting height data as well as above ground biomass data. Next, please. So the overall methodology, if you see, it involves collection of tree height and above ground data from field, and then integration of ICESat-2 and Sentinel-1 data for mapping forest canopy, spatial distribution of forest canopy height, and estimation of forest above-ground biomass using spectral information from Sentinel-2 data only, and in combination with Sentinel-1 and ICESat-2 derived forest canopy height. So this study basically analyzed the effect of including canopy height information on above-ground biomass prediction by the synergistic use of Earth observation data using machine learning approach. So basically, this is the first ever attempt to map the forest canopy height and forest above-ground biomass using this ICESat-2 LiDAR in India's forest. Next, please. So here you can see that the predicted I have generated a map of forest canopy height, as I said, by integrating ICESat-2 data and Sentinel-1 data. And this predicted forest canopy height, this varies from 15 to say 31 meter. And it was observed that a random forest-based model was able to predict forest canopy height with an accuracy of RMSE of, let's say, 1.15 meter. This displays a huge potential of ICESat-2 data for mapping and monitoring of forest canopy height mainly in the tropical forests of India. And above-ground biomass also was predicted. So there are two things. One, relating the field biomass with the spectral information from Sentinel-2 data, and another thing is incorporating the height information in addition to the spectral information. So above ground biomass predicted using only spectral variables and and incorporating the spectral information with the height variables. And we have found that the model consisting of spectral variables only predicted biomass with an RMSE of around 25 megagram per hectare, whereas the model developed by incorporating forest height information with the spectral information created above ground biomass with an RMSE of around 19 megagram per hectare. So this study actually reflected that the incorporation of forest canopy height with the spectral information yielded higher accuracy for biomass, above ground biomass prediction. The study actually highlighted the importance of forest canopy height in above ground biomass prediction. Next, please. So in conclusion, I can say like the availability of ICESat-2 data opens up new vistas for forest biomass mapping and monitoring. Here I would like to highlight mainly for the tropical forest, and the methodology this can be followed for mapping and monitoring of forest above ground biomass and carbon stock. Moreover, this study was done using freely available data, freely available software, and as well as platform. As this can be replicated in other areas very effectively. And this, what I found from my experience, is the ICESat-2 data has huge potential for mapping height as well as biomass for better understanding for global carbon budget and climate, of course, the global climate. So here I must thank my dean and director of my institute. I would like to thank NASA's ICESat-2's early adopter program, because of which I could access these data sets. And I would like to thank Sabrina for her constant support. I'm also thankful to NSIDC for providing this ICESat-2 data. And of course, I'm also thankful to ESA for providing the Sentinel-2 data. Thank you very much.
Excellent. Thanks so much for that presentation. Let's see. So Ross Smith, do we have you out there in Zoom?
Yes, I'm here.
Very good. I'm going to pull up your title slide. Questions? All right. Take it away, Ross.
All right, excellent. My name is Ross Smith. I am the technical program manager at TCARTA Marine. We are a remote sensing hydrospatial company out of Denver, Colorado. Next slide, please. So TCARTA Marine, we've used ICESat-2 effectively since the beginning of the applied user program with ICESat-2, and our focus has been on deriving bathymetry from ICESat-2 and then integrating that bathymetry data with multispectral imagery to really scale up production of nearshore bathymetry or optically shallow water bathymetry mapping. So you can see from these programs here, we have really 3 different programs that we're applying ICESat-2 from. So ICESat-2 Applied Users Program was obviously our first kind of introduction into the use of the data set. We primarily use ATLO3 geolocated photon data product. And that effort was really centered upon the initial investigation of the efficacy of deriving accurate bathymetry data from ICESat-2 with more of a semi-automated, more manual approach, and then initial investigation of integrating it with multispectral imagery. With kind of that efficacy in place, we moved on to employing that into our National Science Foundation grant, which is a grant to employ multiple space-based sensors to really scale up and automate as much as we can the production of nearshore and optically shallow water bathymetry mapping through that intersection. And ICESat-2 has been really integral to achieving the goals of that grant. And then we have our NOAA small business grant as well, which is more of a pointed investigation where ICESat is also an integral component. And as you can see on the right, there has been some media about this. We've definitely been working on shouting about how great ICESat-2 is for coastal bathymetry mapping, and definitely really excited about it. Next slide, please. So this is kind of our first publicized or published data here on the efficacy of ICESat-2. This was something that was performed in conjunction with University of Miami School of Marine and Atmospheric Science, Professor Sam Perkis, Professor Art Gleason. It was published in Frontiers Marine Science Coral Reef Research Journal. And This is basically just looking at the manual extraction of ICESat-2 bathymetry data compared to predominantly single beam echo sounder data and a wealth of reef locations around the world. I believe most of that data was sourced through the Living Oceans Foundation. And you can see very high correlation between what's considered the highly accurate bathymetric product of single beam echo sounder data and ICESat-2, which is really remarkable, given that it's a space-based sensor so high up there and orbiting around us. We have done also our own research on various comparisons of in situ data compared to ICESat-2 bathymetry depths and found around the same results, around 30 to 40 centimeter root mean square error. And so that really gave us kind of the validation of the efficacy of using ICESat-2 point data to calibrate and validate a more continuous surface derivation with multispectral imagery. Next slide, please. So as part of the NSF grant, we're really trying to map the world's oceans, or as much as the world's shallow waters as we can. And a manual approach was not really applicable for that. So the approach we took was to develop a deep learning model. So this is really what's going to enable us to follow us around the world is the readily available as multispectral imagery. We needed to have the same volume of ICESat-2 data intersecting that imagery. So our machine learning engineer, Felicia Nurendwati, did an outstanding job of really developing this model herself as our key heart is sole machine learning engineer, and it's really given us the ability to increase our scale and productivity just substantially. The nice thing about the machine learning data is it matches up really well with our validated manual extraction process, basically getting an R-squared value of 1 compared to the manual extraction, while also greatly increasing our production. As you can see there, almost a 1,500% increase in production rate. And at this point, we have about 150 million ICESat-2 depth retrievals around the world in 6 continents, as you can see on the map on the right there. And while still retaining that same accuracy, as I mentioned before. Next slide, please. And so using this, we've done a couple of pretty substantially large projects with the integration of primarily Sentinel-2 data. We have also used Worldview 2 from Maxar, Worldview 3 from Maxar, as well as Landsat 8, and some other high resolution sensors we've tested out with Satellogics sensors, for example, which is a 1 meter resolution. You can go back a slide if you'd like, thank you. And so you can see we have the Hydrographic archipelago, almost the entirety of the Maldives, which was actually a trial project for Seabed 2030. And then also basically our giant map of the Red Sea we did. And we've really seen that ICESat-2 allows us to achieve depths in areas where we would normally not be able to. There's very limited chart data in the Maldives, and you would not be able to achieve this kind of accuracy of the derived surface. And same goes for the Red Sea as well. Next slide, please. And so you can see here, the efficacy of this ICESat-2 based calibration of multispectral imagery derives some highly accurate derived products as well. When you're looking at multispectral 10 meter or 30 meter imagery, it's a pretty large footprint to be comparing against something fairly accurate and more finite. And we're seeing, across the range of depths you might achieve, you're really not getting a huge drop off in accuracy. And by using these multi-temporal image composites, which allow us to basically compile multiple images together to get a clean surface to work from, we're really able to map large areas and extrapolate this point data across a wide breadth of aerial extent. And I think that's all I have, and you can ignore that questions there, so we'll do them at the end. Thank you.
Awesome. Thanks so much, and apologies for the slide going forward. I don't know what happened there.
That's okay. Technology. Thank you.
No worries. Let's see. Doug Comer, can we hear you out there?
There we go. Yes.
Gotcha. I'm going to go ahead and advance this here and turn it over to you. Take it away.
I'll be happy to do that. I thought this was recorded, but that's all right. So we've been using ICESat-2 to detect archaeological landscapes, and the focal point of our work is actually Micronesia. Some very interesting developments in these very small islands, remote islands in Micronesia, where we see the emergence of highly sophisticated urban areas perhaps some of the earliest stone architecture in the Pacific Islands. What you're looking at here, however, is not Micronesia. We've been using ICESat-2 to detect, as we refer to them as archaeological landscapes, and those can be below water, underwater, or they can be on land. We did a airborne LiDAR survey a couple of years ago at one of our islands called Pohnpei at the World Heritage Site of Namadol. We found terraces. And so this island is covered with enormously heavy vegetation. So one of the things that we're trying to do is to determine whether or not ICESat-2 can be used to detect this kind of patterned landscape, in this case, archaeological terraces. But since it's such, the vegetation there is so heavy, we decided to see if we could detect landscapes, these terraces, in places that were not covered with heavy vegetation, and then work from there. So what you're looking at is actually a place called Pisac in Peru, someplace it's known as the Sacred Valley. And these are ICESat-2 returns, and you can see the steps that actually come up very clearly. We were actually pretty amazed that we could see these stepped terraces so clearly. Next slide, please. Next slide.
Hey, Doug, your presentation is pre-recorded. Should I play it forward until the slide changes?
You could do that, yeah.
Try that.
Do that, yeah.
Bear with me. Forward. Oh, there we go. Is that the next one?
Yeah.
Perfect.
So is this going to play, or do you want me to continue to talk?
So I can either hit play or you can speak to it. I've paused it on this slide. So why don't you just talk to it?
Okay. All right. So as I mentioned, our area of interest is really Micronesia, in particular, two of the islands in Micronesia, which display this really early example of stone architecture. Maybe what we're looking at here on the left is the island of Pohnpei, which has the archaeological site, World Heritage Site called Namadol. And this particular site might have the earliest stone architecture in the Pacific. There are about 25,000 islands in the Pacific. So the mystery has always been, why in the world would it emerge here first? And it seems to have something to do with the fact that there was archaeological terracing that nobody knew anything about until we did the airborne LiDAR survey a couple of years ago. Now the question is, what else is there? Now, to get an airborne LiDAR survey accomplished, of course, you've got to get the platform out to these very, very remote places, and that's can be expensive and complicated. And with COVID, it's impossible at this moment in time because they don't have COVID in Micronesia, and they're not allowing people to come in. So again, what we decided to do is to see if we could find patterns from returns from the ICESat-2. And we've used these, two different products to do that. Let's just go to the next slide here. And the other thing, well, this is pretty well established. We've done bathymetry using the ICESat-2. Basically there's spot locations, and based on watercolor changes and so forth, you can come up with a pretty accurate bathymetric model. And for us, what that has a lot to do is whether or not they engineered the shoreline in order for the marine environment near these centers of political and ritual influence to be more productive. And this, what you see here is that gap. So the bathymetry is something we've been working on We've been using Sentinel-2 plus the ICESat-2 data to map the bathymetry so far, but we're also going to be using Worldview 3, the Maxar, stuff too, and probably some small sat imagery to see if we can improve that. And then in the lower right-hand corner, again, we see the returns that we're getting from the terraces at Peru. And again, we went to Peru because these are areas where that were not covered with heavy vegetation. Next slide. And this is not.
My bad. I gotcha.
Yeah. A little bit farther. All right, so you see that we've got a nice track across this area of interest. This is the World Heritage Site of Namadal. It's offshore of this island called Pohnpei, and we have a nice ICESat track through this area of interest. I don't know if you can you see my cursor? This is actually this amazing archaeological site. It's about 1 kilometer long and a half kilometer wide. And there are about 100 humanly constructed islands on this reef flat here. And on those islands, there's some really sophisticated basalt structures. And again, it could be that these are the earliest stone structures in the Pacific. All right, so what you're looking at here above Namadal per se is the island of Timwin, which is a sub-island of Pohnpei. And if you look closely, you can see what we saw, which is that there are agricultural terraces there. Now, agricultural terracing is strongly associated with complex, sophisticated societies because you have to have a sizable labor force, and they have to be very well organized in order to, create this kind of a terraced landscape. So what we're trying to do now is to figure out if we can use ICESat-2 returns in order to see if there are other places in this. This is one of the sub-islands of Pohnpei. This is called Timwin. It's like a little archipelago. Are there other places on Pohnpei that contain these kinds of terraces? We're not going to get the kind of resolution that we get from airborne LiDAR, but we're hoping that we can develop a model that suggests where these places are. So that's where we are right now. And we're in the process of writing algorithms that would enable us to discern these terraces beneath the very dense vegetation. One of the ideas that we have is just subtracting the Copernicus dim from these returns from ICESat-2. It's moving along quite well, quite promising. Thank you.
Great. Thanks so much to all 4 of our speakers. Oh, and we do have a closing slide there. Very cool. Let's see. At this point, could we take the slides down, Wayne, and bring up the Zoom so we can see everybody's faces online who chooses to have a camera on? Thank you. And Molly, do we have any questions in the chat we want to start with?
Sabrina. Yes, I'm here. So we don't have any questions in the chat right now, but I do have a question for our speakers. I guess the goal of applied sciences is really to be able to understand, what is that final end use? What does it take for you to operationalize the data, or integrate it to inform a specific application? So could each of you maybe comment on, what you see as has been, I guess, the greatest challenge in operationalizing the data, and if you're not there yet, what does it take, and what sort of timeline are we looking at in terms of actually, moving towards a sustained use by either yourself or your client or your end user. And maybe if we can start with, I guess, Ross, who is already at, a sustained use of the data product. Maybe if you can talk about your clients and how that has been for you.
Sure, absolutely. Well, I can touch on both. In terms of use of the data and getting it to the point where we obviously have been able to use it very, very broadly and efficiently, was that, it's really not designed to be a marine remote sensing sensor, and neither are the data products. It's not in the original mission for it to be, a bathymetric LiDAR, although the wavelength laser is very good for it. So a lot of our challenges, to get it to a product or something we could use was around mitigating all of, the things that come with that, refraction and noise in the water column and variable water column conditions and datums and things like, all the different things that go into making it a marine product. But our technical team has done a really good job over the last 3 years or so at getting it to a place where it's really in a good place. There's more things to be done, qualifying the accuracy or the uncertainty of a measurement, perhaps using other metadata that's available, maybe in the ATL02 product is kind of where we'd see going next to make it even more powerful. In terms of our clients, that Seabed 2030 project, for example, would not be possible to achieve those accuracies or that extent of that data without ICESat-2 point measurements, quite frankly, without spending millions or hundreds of millions of dollars in sonar measurements to get the same data density. So that's really been the application of ICESat-2 has been significant in that realm. Yeah.
Wonderful, thank you.
Can I ask a question about that to Ross? Actually, I'm wondering about the bathymetry. How deep are we talking about with the?
So and it kind of depends on where you are, but and on average we go down to 20 meters. Really good would be around to 30 meters, and really optimal conditions we've seen almost down to 40 meters, but that's rare. Maybe out of the 150 million points, we have maybe 100 points that are that deep. But 0 to 20, 0 to 30 is around average.
Great, thanks.
And Doug, how about you? So what would it take for you to be able to use this information, fused with the other data sets to, protect the World Heritage Sites?
More data, more data. If you could just point these, collect more data over our areas of interest. That would be nice. The more data we have, I think the more reliable we can consider our results as we try these different approaches to finding out how to remove the vegetation. In other words, we want to see, we're going to get these different returns, right, over these very densely vegetated areas. And there are a number of ways that we're thinking about using other data products, to essentially remove the vegetation so we can see if there are patterns that we can at least detect. We'll never get, we're not going to get the sharp imagery that we got with airborne LiDAR. We know that. But there's probably a way to use some algorithm to understand or to find areas that probably contain these kinds of, patterned landscapes, which would be terraces. And also, I think we could probably do clusters of structures too. This area of Micronesia that we're working in is so interesting because we just get these clues that this is a place where these very complex societies emerged. It's way the heck out in the Western Pacific. Everybody knows about Hawaii, but this stuff seems to have developed out in Micronesia before Hawaii and the other islands that we know about. So, but it's all under this dense vegetation. So if we had more data from ICESat-2, we'd have more to work with.
Thank you, Doug. Okay, and maybe Subrata, in your case, you're trying to get this information to the forest department in Assam. So, what does it take for that to happen?
Yeah, whatever I showed is basically, I took actually 2-3 study areas initially when I applied for this early adopter program. One of the area was this moist deciduous forest foothills of India, Himalayan foothills, what I showed. Now I am trying for this largest mangroves formation of India. This is Sundarban mangroves. Of course, the Indian part, not the Bangladesh part, because I don't have like field thing there. So yes, earlier I was trying to for someone who can give some field information about that area also. But my experience with these areas excellent, like with the ICESat-2 data. But this is like relatively flat kind of area or undulating terrain. But now what I am trying to, because I had to test the data in a relatively easy area or accessible areas where I can get more this thing. Moreover, it was COVID time, so in that COVID period also I could go to field, and because it is within the state and it is near to my place where I work, so it is around within 15 kilometers. So, and we don't have to change the district as well. So that was advantage. I could go with with office vehicle, only one person, and collect the field data and come back. So it was a difficult period. The place which you are referring here is Northeast India, which is my main focus. In northeastern part of India, people practice shifting cultivation or slash and burn. So my this thing is, since this data set is there, my purpose was to study the disturbance and recovery. And how to integrate this data to study the net carbon loss or gain from the system. Of course, it is loss only. This kind of studies are not yet been done because there is no data at all. First of all, there is airborne LiDAR data over India is there. It's some parts, but it is very restricted. Even for us, our organization only do this kind of thing. But for us also, there is only a restricted part. We will get the data. But these kind of data sets like ICESat-2, when we're getting, but of course it's not wall-to-wall data we're getting like airborne, but yeah, we can integrate with other data sets to get a similar kind of information. So now I'm moving towards a larger area, or like say, you can say, a problem specific thing. And moreover, I'm now trying to, as I said, maybe this month I'll be, completing about mangrove thing, because this is very interesting. Sundarban mangroves, there was one of the largest mangroves in the world, formation in the world. And then I was trying to generate a canopy height map of whole India. The problem is, like, when you use so many data sets, it is very difficult to control with R even. So this is the main problem I am facing now. I've done away with outlier removal, everything I have done. Only thing, generating this kind of map and generating information, I am getting difficulty in that. It is because this huge data set, if you take Indian whole Indian context. So my aim was to generate a height map of India, forest canopy height map of India, which could be very much beneficial for the biomass estimation, because till now biomass map, whatever you see in Indian context, these are basically based on spectral information. That means we are looking for only in the reflectance. We are forgetting about the 3D information of the forest. So no structure or the height information is incorporated in the biomass estimation. So of course, in this small study, what I have found that when you incorporate height information in addition to spectral information, that you get better accuracy. So maybe like we are planning for January to visit northeastern part of India, because I basically come from northeastern part of India only. I work here in the northern part. So if situation is now, it's fine, but you never know what happens. But yeah, my future plan is to study using this kind of, since there is a repetitive coverage also. I would like to study this heavy, very dynamic system called shifting cultivation or the slash and burn practice in the northeastern part of India. Can I study the disturbance recovery and disturbance recovery vis-a-vis the carbon loss or gain from the system? And to a larger picture, generate a forest canopy height map of India. This will open up many things. Like, people are waiting for this kind of information for various purposes. Maybe a few people are looking for habitat modeling also. They need the height map, but they don't have. So this kind of information will be very good information for any user.
Okay, all right. Thank you for that insight. And Neil, finally, how about yourself? How do you see this?
No, Yeah, NOAA will continue to use ATLO3, any data you give us. The latency is okay at the moment because we have a cycle for how often we produce nautical charts. We use the ICESat-2 to supplement our data collection and to access hard areas. And because there's so much shoreline and water that we're responsible for, or NOAA's responsible for, we have to automate. So that's our main effort at the moment. And so we feed the data into that, and then we just turn the gears, if you will. However, let's say a hurricane comes through the Keys or any port that has a cruise industry, and you know, the channels get blocked up by shifting sands and so forth. Then if we had faster access to ICESat-2, we could take a look at that data almost immediately, and we wouldn't have to move a ship from one location to another. So we're thinking down the road. I know you're going to solve this problem. So that's something we're looking forward to. But in general, I think NOAA's responsible, you know, for all the shoreline and waters around the coasts and territories. And so it's a lot of work. But yeah, we're excited to move forward.
So,
Molly, go ahead.
all right, so I'm going to read a question that we have from online. Thank you for that. And there are 3 upvotes, so it's excellent. So the question is to the group. We just saw 4 great applications of how to use ICESat data. The satellite's name, however, suggests that it's made mostly to map ice. Can you summarize the capabilities of ICESat-2 to map glaciers, especially when compared to other existing satellites? And I think it's to you, Tana. Very good.
Not allowed to ask me questions. It's the Applied Sciences Town Hall. I'm kidding, of course. Yeah, as the name implies, it really is optimized to measure changes in ice sheets and sea ice, as well as glaciers. The challenge with glaciers is often that they are steep and they're lumpy and they're covered with dirt, and sometimes they're covered with water. And all of those things make it really hard to measure the height accurately. However, yeah, there hasn't yet been at least that I've seen, a comprehensive look at glaciers around the world using something like Randolph Glacier Inventory or what have you. A few test cases show that as our version numbers have increased, the improvements in the geolocation really helps with the height measurements and height change measurements over these glaciers. However, our off-pointing plan that we use in the mid-latitudes to get better coverage over vegetated areas works against us in trying to measure height changes over glaciers, because we're not repeating those tracks exactly, and instead we're relying on these crossovers. So yeah, I haven't seen a whole lot in the peer-reviewed literature yet, but I'm sure it's coming. As many of our speakers have said, as we collect more and more data, there's more and more things you can do with it and fill in a lot of those gaps. So yeah, that didn't really answer the question, but I used up 4 minutes. What?
Could I ask a question? I'd like to ask Dr. Nandy. So, I mean, this is really interesting to me that you're merging Sentinel-1 with ICESat-2 data to gauge biomass, right? You're trying to characterize biomass. Exactly. I mean, how does that? Are you using some of the returns from the ground as like the lower parameter, and you're using Sentinel-1 for the canopy? Is that how you? I mean, is that
yeah. Basically, there are 2 parts in that. One is generating the height map for canopy height map.
Mm-hmm.
What I am doing is we have LiDAR footprints and ATL8 data, 08 data,
Mm-hmm.
and in that this is integrated with Sentinel backscatter, like VVVH, and the texture information out of that data. So one is backscatter and texture information is gray level co-occurrence matrix. So texture as well as backscatter, and relating these two with a machine learning based algorithm to generate a forest canopy height map. Now this is one part. Second part, what I am trying to doing, and then of course we are relating this to verifying this whatever model output we have got. We are verifying this with field data as well. Now after that, we are laying field plots in field and calculating biomass from field. Now those are point location again. And then we are trying to do, biomass as a dependent variable and spectral variables from Sentinel-2 data as independent variables. We are again relating and getting the biomass map. This is what we used to do. Now here, what we have done is spectral information is fine. One model is with spectral information. Another model is spectral plus that height map, which we have generated using Sentinel-1 and ICESat-2 data. So what we have found that the moment you include that height information in that, so you are getting a better estimate of biomass rather than when we are using only spectral information for biomass info for this thing.
Great.
Yeah.
Great, that's great. If you have anything written up about that, I'd love to take a look at it. It's fantastic. Yeah.
Thank you so much.
Wonderful. So I think we have 4 minutes, Molly.
What? One more time?
I think we only have 4 minutes left. Are there any other questions? I can ask one more, but I don't know if we have enough time.
I think we should wrap it up there, Sabrina.